Hello, welcome back to the second course in physics, and we are still dealing with magnetic fields and currents. In this lecture, we will continue the discussion of the magnetostatics topic, and in particular, we will be talking about the magnetic fields set up by currents. And this will be the first lecture of this type. And the contents of this lecture will include some general introduction. Then the force between two currents will be addressed. Laplace force will be defined. The law of Biot-Savart for the evaluation of the magnetic field due to a current carrying conductor will be addressed. And then we will apply this law of Biot-Savart to evaluate the magnetic fields in different configurations. The final topic of this lecture will be to derive a formula for the divergence of the magnetic induction. And to begin with, we start by recalling that experience and experiments have shown that electric currents exert force on each other. So if we have two currents or two current-carrying conductors, they interact with forces. And this can be interpreted by recalling that a current-carrying conductor existing in a magnetic field experiences a force. So that way, the interaction between two currents can be interpreted as due to the effect of the production of a magnetic field by one current that influences the second current. So as a conclusion, we can say that moving charges or currents produce magnetic field, just like electric charges produce electric fields. So charges in motion would produce both electric and magnetic fields. And now we talk about the forces between two currents. Here we take the most general case where if we have two loops of arbitrary shapes, loop A and loop B, and loop A is carrying current A, and loop B is carrying current B, and we would like to evaluate the force of interaction between these two currents. Of course, the force acting on one is exactly the same as the force acting on the other, but in opposite direction, because it's like an action-reaction pair. So in order to do that, we consider, for example, an element of length of an element of current of loop A, DLA, carrying current IA, and we consider an element of current of loop B, DLB, both magnitude and direction, which has direction and magnitude, carrying current B, and we consider the force of interaction between this current element DLA and the current element DLB. This force is simply mu naught over 4 pi times the current IA times the current IB times the length of the element DLB cross the length of the element DLA cross R, which is the position vector of DLB with respect to DLA, over R cube. That is the force that the element DLAB exerts on DLA, or vice versa, of course. They just differ by the direction. we see that the force is proportional to the currents and proportional also to the lengths of the elements, and it's inversely proportional to the square of the distance between them. And in order to evaluate the total force that loop A influences loop B, we have to do the integration over the loop A, where we evaluate the total force that loop A affects on the element dLB, and then we integrate over dLB over the length of the loop B in order to obtain the total force that the loop A is influencing loop B. So we have some sort of a double integral. One is to evaluate the total force of loop A influencing an element in B, and then we integrate over loop B to have the total force from loop A acting on loop B. And this is the formula. And now we can rewrite this formula in the following form. If IAB, we can perform, first of all, the integral over loop A to obtain the magnetic field produced by loop A. And this integral is mu naught over 4 pi IA times the integral over A, over loop A, dLA cross R over R cube. That gives the field produced by loop A. And then the force is simply that loop A influences loop B is simply IB times the integral over B times dLB cross this field produced by loop A. This is a general form that is applicable to any shape and any current carrying conductor. Thus, we just modify the equation, and we get if AB is equal to IB integral over B dLB cross the integral of mu naught over 4 pi IA dLA cross R over R cube, and that can be rewritten as if AB is equal to IB times the integral over loop B dLB cross the integral over loop A of dBA, where the integrand here inside the integral over A is dBA. It's the element of the magnetic induction produced by an element dLA of loop A. So this is, as we mentioned a little while ago, this is simply the magnetic induction produced by loop A. So it's this gives us a similar formula to the one that is produced that is talked about previously, which is the fact that a current carrying conductor in loop B is influenced by this force due to some magnetic field that is produced by another current which is in loop A. And this would lead to the derivation of Laplace force, which is a restatement of the same result that we have just reached. The force exerted on a current by a magnetic field is thus written as this: F sub L Lorentz sub Laplace is equal to IB times the integral over the loop B dLB cross B, where B is the magnetic induction produced by some agent, by something, at the location of the element dLB. And we do the integral over the loop B, and that will lead to the evaluation of the full force, of the total force acting on loop B due to a magnetic field produced by by something, by a method or another. And here we consider that it is produced by an electric loop. by an electric current. This can also be rewritten using the definition of the current and the current density. If we recall that the current density J is simply I divided by the cross-sectional area. So I is simply the cross-sectional area of the conductor carrying the current times J. So if we carry the direction of the current, instead of putting it in the direction of dl, if we put it as a direction of the current density, because the current density is a vector with a direction, now the direction is carried by J rather than by the length, then we will be left by dl times the cross-sectional area. dl times the cross-sectional area is simply d tau, which is the element of volume. So this will be rewritten as J, the current density, cross B times the element of volume carrying the current density J. And if we integrate this quantity over the volume of the conductor, this will give us the total force acting on the conductor. And this is just another formulation of how we calculate the force. But it's similar. It's the same as the previous, as the previously mentioned force laws. And now we come to the question of what is, we have talked about the fact that a current can produce magnetic field in the region surrounding the current carrying conductor. Now the question is, what is the magnetic induction produced by a current carrying conductor in its region? This can be evaluated. The magnetic field produced by a current can be evaluated by the so-called Biot-Savart law, which is a law that is concerned with the determination of the magnetic field from that is arising from a current. So if we have a conductor or a wire carrying current I, and we are interested in calculating the magnetic field at a point P from that wire, so we take an element of length dl, and this element of length, of course, a current I, the current I is passing through it. And if we want to find the magnetic field at point P, then the field produced by this element of length is dB. It has both magnitude and direction. And this dB is given by mu naught over 4 pi times I, the current, times dl, this element of length, cross r, which is the position from dl to the point of interest, P, divided by r cubed, the distance between the element of current and the point P of interest. And where mu naught is the permeability of free space, and it is given by mu naught is equal to 4 pi times 10 to the minus 7, and the units are Tesla, meter, per ampere. This is the permeability of free space. Of course, we are measuring the magnetic fields, or we are creating magnetic fields in empty space where the permeability is mu naught. We are not considering magnetic materials. And now this field that we evaluated, what are the characteristics of this field? If we recall the formula by which we can calculate the field, it is proportional to the current I, of course, and it goes like dl cross r over r cubed. So one of the characteristics of this field produced by a current is that the field follows an inverse square law, because we have r here and 1 over r cubed, so it goes like 1 over r square. So it's like an inverse square law force. And also the direction of the field that can be seen from the formula also, the direction of the field is perpendicular to the plane that is defined by the direction of the current, dl, and by the position vector, r, to the point at which we are evaluating the magnetic field. So basically, if we have a current flowing in a direction, and if this is the current, and this is the where we are evaluating the field at this point, so the magnetic field goes like dl cross b. That means it is perpendicular to this plane. So it's pointing either in a perpendicular to the plane, either this way or this way, depending on what's the direction of dl cross b. That goes according to the right-hand rule, where we can put our fingers from the direction of dl, the direction of the flow of current, and turn it towards r. And that would be the direction of dl cross r. So these are characteristics of the field. And that way, we can see that if we have a current going upward, for example, in a wire, then we can put, if we can put our fingers and our right hand such that our thumb is pointing towards the in the direction of the current, then our fingers, as they turn around this around the straight wire carrying the conductor, carrying the current, would be in the direction of the magnetic field. Thus, the magnetic field would be azimuthally, like forming circles around a straight wire carrying the current. So the magnetic field of a long straight wire can be now determined both magnitude and direction. And if we consider that we have a straight wire carrying current I, then the magnetic field, from the definition from Biot-Savart law, it's mu naught I over 4 pi times dl cross r over r cube. But we are interested in the magnitude. First of all, we evaluate it, and then we take the magnitude. So it's like mu naught I over 4 pi times sine theta dz over r squared. How did we get that? Actually, if we consider dl, dl is in the z direction, and this is r. So dl is simply dz. Cross r is simply dz times r times sine the angle between them. And the angle between z and r is considered theta. So we have r times dz times sine theta. And r eliminates one of these powers of r. So we are left with sine theta dz over r squared. It's an inverse square law, as we say. And since now we can substitute the values r, since r is variable, we can replace it by the position along the wire by z. Small r is equal to the square root of r, capital R square, plus z square, where z is the position of the element of the current that we are evaluating. And now we can evaluate over z, we can integrate over z over the length of the whole straight wire. Notice that sine theta, also we have to replace sine theta in terms of z, because we are integrating over z. Sine theta is the same as sine pi minus theta. That means sine theta is sine this smaller angle, pi minus theta, which is equal to r divided by small r. Small r is square root of z squared plus r squared. And that gives b is equal to mu naught I over 4 pi times r dz over z squared plus capital R squared, all to the power 3/2. And we evaluate this integral over z, and the result is simply mu naught I over 4 pi capital R times z over z squared plus r squared to the power 1/2. And this is evaluated for a long straight wire. Long straight wire, that means it's an infinite wire. So it extends from z equals minus infinity to z equals plus infinity. That is true for a long straight wire. And the result of this, if we substitute for z from minus infinity to plus infinity, you have to remember that when we set z equals to infinity, then r can be eliminated because it's very small with respect to infinity square. So we are left with z over z, and z over z is just 1, simply. So we have mu naught I over 4 pi r from this limit, and we have mu naught I over 4 pi r from this limit. So we are left with mu naught I over 2 pi r, twice as much as the value obtained from one limit. Each half of the wire would give mu naught I over 4 pi r. And the two halves would give you this mu naught I over 2 pi r. So we can keep that in mind, this result in mind. This formula was, for the long straight wire, was derived by Bayer and Savart in the year 1820. And the field near one end of a semi-infinite straight wire is half this value, as we just mentioned. It's just if we take the limits from 0 to infinity, for example, or from minus infinity to 0, rather than the same integral before. You just take the limit from 0 to infinity, rather than from minus infinity to plus infinity. We will obtain B is equal to mu naught I over 4 pi r. So if we have a semi-infinite wire, straight wire carrying current I that extends from 0, from this point, to infinity, at a point, a distance r from the end, from one end, the magnetic field induction is of that strength. And the general result is if we consider that the wire is finite in length, that extends from one end at position z1 to another end at position z2, then the same integral that we have obtained before gives B is equal to mu naught I over 4 pi r times this quantity z over z square plus capital R square under square root. But this is now evaluated between z1 and z2 rather than between minus infinity and plus infinity. And if we substitute for z here in the integral, substitute for it z1 in one limit and z2 in the other limit, then we can find the magnetic field produced by a straight wire carrying current I if the straight wire has any length that we wish. This is a general form. And now we go to the application of Bayer-Savart law. And as an example, the field at a perpendicular distance r from one end of a finite straight wire of length L. Let's assume a finite wire of length L, and so we substitute in the previous result for the integrand. In the integrand, we substitute the integral from one end, which is from minus L over 2 to plus L over 2. That's where the wire extends, and the result of the sorry, if we are measuring the field near one end of the wire, so we assume that one end is at z equals 0, and this end is at z equals L. So the limits of the integral would be from 0 to L. And if we take these limits and we consider the same integral that we have performed before, the result is mu naught I over 4 pi r times L over L square plus R square under root. And the other limit at z equals 0 will give us 0 result. So this is the result of a finite wire, the field induction due to a finite wire at a distance r from one end in a direction perpendicular to the length of the wire itself. this is a direct application of the case that we have discussed before, the general case. And now, as a second example, we consider the same wire of length L, but now if we are interested in finding the magnetic field at a distance capital R from the center of the wire in a direction perpendicular to the length of the wire, just like the way it looks in the figure, we recall the same result that we have obtained from the general result, from the integral, and we take the limits from z equals minus L over 2 to z equals plus L over 2, and the result of the previous from the previous formula, if we substitute z1 equals minus L over 2 and z2 equals L plus 2, L over 2, then we obtain the magnetic induction, in this case, at a distance r from the center of the wire is equal to mu naught I over 4 pi times capital R, all multiplied by the length of the wire L over the square root of L square over 4 plus capital R square. And this is the formula for the magnetic field at the center. Although it looks a little bit complicated, but it's straightforward if we know how to use Biot-Savart law to evaluate the magnetic field due to current carrying conductor of a certain geometry, and if we know calculus, if we know how to evaluate integrals and limits of integrals. Now, we encounter the issue of the direction of the magnetic field. The previous examples were focusing on the magnitudes of the magnetic field produced by a straight wire carrying a current. And now, what about the direction of the magnetic field? The field lines around the straight wire. How do they look like? Now, we know that around the wire, due to the symmetry of the shape of the straight wire, there's azimuthal symmetry, meaning at a distance r from the wire, it doesn't matter where we are around the wire. So there is, we can draw a circle around the wire, and at each point in that circle, we should get exactly the same magnitude of the magnetic induction. So there is azimuthal symmetry. So that means the magnetic field produced by a wire carrying a current, the magnetic field should make concentric lines around the wire. Because the magnetic field direction is always directed in a perpendicular direction to the current and to the position. So if this is the position and this is the current, we have dl cross r. So at this point, the magnetic field is directed that way, and at that point is directed that way, and that point directed that way, and so on. So it makes like circles around the current. So if we point our thumb, as I said a little while ago, in the direction of the current, the direction of the magnetic field around the wire will be going in the direction of the fingers of the right hand. And the density, these field lines will be stacked around the wire in circles, in circular forms, and the density of these lines will go as 1 over r. That means if we get farther away from the wire, then the field lines, they get spaced out more, which means that the intensity or the strength of the magnetic induction is lowered as we go farther away from the wire, which makes sense because the farther away from the influence we get, the weaker is the influence. Now, the field due to current in a circular arc can be calculated easily because of the geometry of the arc. If we consider an arc, as shown in this figure, that carries current I, and we are interested in finding the magnetic field at the point C, where point C is the center of the circle from which the arc is cut. So that point C, that means it is at the same distance, from all points or all elements on that arc. So R is fixed in magnitude. Now, what remains is the direction of the magnetic field produced by each element on that arc. Again, from Biot-Savart law, we notice that the direction is always I in the direction of I, dl cross R, the direction of the current flow cross R. R is the position from the element of current to the point where we are evaluating the current. So that means the direction of the magnetic induction at point C is directing inward towards the plane, towards the page. And that's why it is symbolized by a cross here at point C. And the magnitude of the field is mu naught I over 4 pi times dl cross R. That means dl times R times the angle between them. And the arc is making an angle 90 degrees with R, with the position vector. It's always 90 degrees. So sine 90 times dl times R over R cube. R over R cube is simply 1 over R square. And since R is constant, so that gives mu naught I over 4 pi R square times the integral over L. The integral over L is simply the length of the arc. And the length of the arc is simply R times the angle phi in radians. The radius R times the angle phi in radians is equal to the length of the arc. So again, phi times R over R square is simply phi over R, and the result is B is equal to mu naught I times phi over 4 pi R. Now, this result is correct for the arc of any length. We just have to substitute for phi, which goes for the length of the arc. So this result is true for any circular arc. As an example, if we consider a circle, the circle is an arc where phi is equal to 2 pi. Phi, the angle subtended by this arc, is equal to 2 pi. So if we go to the previous formula for B for an arc and substitute for phi, we put 2 pi instead of 4 pi. We have mu naught I over 4 pi R times 2 pi, which is phi. That gives mu naught I over 2R. So the magnetic field at the center of a circular loop carrying current I is equal to mu naught I over 2R, where R is the radius of the circular loop. And what is the direction? What is the direction of the magnetic field at the center? The direction is obtained by, if we are running our fingers in the direction of the current, if we are running our fingers along the loop in the direction of the current, then the direction of the thumb gives the direction of the magnetic field at the center of the loop. So that way we obtain both the direction and the magnitude of the magnetic field produced by a current loop. Also, as an example, we can look at this shape where it consists of two semicircles, one arc which is a semicircle, half of a circle, of radius b, and another half a circle of radius a, and those two halves are concentric, and they are connected by wires, and they are carrying current I. This could look complicated, but actually it's not, because we can apply the same formula that we have obtained before. That is, the magnetic field produced by an arc is simply mu naught I over 4 pi times r times phi, which is the angle subtended by the arc. So in this case, in both cases, the angle phi subtended by the arc is simply pi. It's half a circle. It's pi. But in this case, r, which is the radius of the arc, is different. So we have the first arc has a radius of b, which is larger than the second radius, which is a. Since the same current is carried by both arcs, then the magnetic field produced by the smaller arc of radius a, which is magnetic field produced upward, is in the direction of outside the page. That field is larger than the field produced by the larger arc of radius b, and the field of the due to the larger arc of radius b is directed according to this convention or way of determining the direction of the field. It's directed inward into the page. So we have two components of the field, one pointing outside the page and one into the page due to the arc b, and in each case phi is equal to pi. So we substitute all of these things, and we find b is equal to mu naught I over 4, and phi is equal to pi, reduces the pi that was here, and we have 1 over a, which points upward from the inner semicircle, and minus 1 over b, because the field due to the b circle arc is inward into the page. So this is the total or net field produced at the center of this wire, which consists of two concentric semicircles. And now we can evaluate the field on the axis of a circular loop, a distance z from its center, and we take the loop now this is the loop of radius a, and we are interested in calculating at its axis at a position z, far away from its axis, from the center at its axis. And we recall Biot-Savart law, and we recall that the magnetic field is at every point makes a vector that is perpendicular to both r and the current element. It's like this. So this can be decomposed into two components. One component is planar component in the plane, and the other component is in the z direction. And as we go around the loop, the planar components, they cancel each other because they go around the loop in planar. They change the direction, they cancel, and the only component that adds up is simply the z component. And the z component is b is equal to mu naught I over 4 pi times the integral of sine theta times dl over r square, and sine theta is a over r, where r is the distance between the point of interest and the element of the current, and is equal to the square root of a square plus z square. And putting these together, taking into consideration that the distance r is always, or a square plus z square is always constant, we can find that b is equal to mu naught I times a square, the radius of the current loop, square, divided by 2 times, in parentheses, a square plus z square to the power 3/2. And notice that if we set z equals to 0, we obtain the same result that we obtained previously for the magnetic field at the center of the loop. If we put z equals to 0, that's simply the center of the loop. And we get simply mu naught I over 2a, which is the same result as obtained before. And in the limit as z goes to infinity, that means if we have a loop and we are interested in evaluating the magnetic field far away from the loop at the axis, at z much larger than the radius of the loop, then z is much larger than a, and we can eliminate a in the brackets in the denominator, and we obtain b is equal to mu naught I a square over 2 z cubed, which is mu naught over 4 pi, we multiply by 2 pi over and above, times 2 I pi a square over z cubed. This is just a modification of the form, and thus b is equal to mu naught over 4 pi times 2 times m over z cubed, where m is equal to the current I times the area of the loop. M is the magnetic dipole of the loop. So the magnetic induction is inversely of the loop of a magnetic dipole at the axis of the dipole, of the magnetic dipole far away from it, is inversely proportional to the cubic distance from the center of the loop. And now the divergence of the magnetic induction, it's worth mentioning that if we have a current carrying conductor, we consider the element of volume d tau carrying current J, and we are interested in evaluating the field at a point R from that current. If we also recall Biot-Savart law, B is equal to mu naught over 4 pi times I dl cross R over R cubed as usual. And also we have I dl is equal to the current density J times the cross-sectional area times the length dl. And if we move the direction to be carried by the current density J, so this is equal to J, the current density, times the volume element. Putting these together, we obtain B is equal to mu naught over 4 pi times J cross R over R cubed integrated over the volume. And now div B is equal to mu naught over 4 pi times the divergence of this quantity in the integrand. And we evaluate this divergence. We notice that the divergence of J is equal to 0 because the coordinates of the divergence are different than those of the coordinates of J, and the divergence of this quantity R over R cubed is equal to 0 by calculation, which will lead to div B is equal to 0. And div B equals to 0 means that the flux over the surface or any closed surface surrounding a bar magnet is equal to 0, and that means that we have no magnetic monopoles. Magnetic monopoles do not exist in the universe. And I thank you at this point for your attention. I end my lecture.